Hello everyone, welcome to today's session. I'm excited to share with you the 20 important Java interview questions with answers. This is part of our core Java interview series, and today is day 2. In this presentation, we'll cover key questions that frequently come up in Java interviews, along with clear, concise answers to help you prepare effectively. Let's get started. Let's break down these components. First, the JVM, or Java Virtual Machine, is responsible for executing Java bytecode. Think of it as the engine that runs your Java programs. Next, we have the JRE, which stands for Java Runtime Environment. The JRE includes the JVM plus the necessary libraries to run Java applications. So, it provides everything needed to execute Java code, but doesn't include development tools. Speaking of development tools, that's where the JDK comes in. The JDK combines the JRE with additional tools like JavaC, the Java compiler, which allows developers to write and compile Java code. Now let's connect this with a real-world example. Imagine a developer writing a Spring Boot application using the JDK. When that application is deployed on a server, it runs using the JRE, with the JVM executing the bytecode. For instance, a banking backend application running on a production server. Finally, to clarify the key difference, the JDK is for development, writing and compiling code, while the JRE is for running applications, and the JVM is the engine that actually executes the Java bytecode. Understanding these distinctions helps us see how Java tools fit together in the overall development and deployment process. A class is essentially a blueprint for creating objects in Java. Think of it like a template that defines what an object will look like and how it will behave. It contains variables, which are also called fields, and methods, which are functions that define the actions or behaviors of the objects created from the class. Now, to bring this to life, let's consider a real-time example from an e-commerce application. Imagine we have a class called Product. Inside this class, we might have variables like the product's name, which is a string, and its price, which is a double. These variables describe the attributes of a product. The product class then provides the structure for all kinds of products, whether it's a laptop, mobile, or TV. Each of these specific products will be an object created based on the product class blueprint. So when we ask, what is a class in Java? The key idea is that it's a way to organize and define data and behavior together, so we can create multiple objects that share the same structure and functionalities. This concept is fundamental because it helps us build more organized, reusable, and manageable code in our applications. All right, let's talk about what an object really is. An object is essentially an instance of a class. Think of it like a specific example or a concrete version of a blueprint. It represents a real-world entity that we might encounter in everyday life. For example, if we have a class called Product, then an object of that class, say P1, would be a particular product, like an iPhone 15. When we create P1, we're giving it its own specific data and behaviors, which means it has a state, like its price, color, or model, and behaviors, like being able to ship or display details. Now, to connect this to real-time use cases, imagine you're shopping online. When you add a product to your cart, what you're really doing is creating an object, say P1, that holds all the information about that specific product. This idea of objects helps us organize and manage the complexity of real-world entities in a way that makes sense within our code. So, to sum up, an object is a tangible instance of a class, representing something real or conceptual, with its own data and behaviors. It's a fundamental concept that helps us structure and understand our programs better, especially when dealing with real-world systems like online shopping. Inheritance allows one class to acquire properties and methods of another class, using the extends keyword. Think of it as a way for a new class to build upon an existing class, gaining its features automatically. In the real world, this is especially useful in systems like banking. For example, consider a basic account class that has a balance. Then, a savings account class can extend account, meaning it inherits the balance property. Additionally, it can have its own features, like an interest rate. This way, all account types share common features like balance management, making our code more organized and efficient. So, in summary, inheritance helps us reuse code and create a clear hierarchy, which is essential in building scalable systems. Polymorphism allows methods to perform different tasks based on the object calling them. Essentially, the same method name can have different behaviors depending on the context. For example, think about method overloading and overriding. These are two ways polymorphism manifests in programming. Overloading lets us define multiple methods with the same name but different parameters, while overriding involves redefining a method in a subclass to suit a specific need. Now let's consider a real-time use case, like a payment system. When we call the pay method, it can represent different payment types. For instance, it could process a credit card payment, a UPI payment, or net banking. The key point here is that the same method, pay, behaves differently depending on the payment method chosen. This flexibility is what makes polymorphism so powerful, especially in designing systems that are scalable and adaptable. So, to sum up, polymorphism lets us write more generic and reusable code. We can invoke the same method name, but the actual task executed depends on the specific object. This is a fundamental concept that helps us create more dynamic and flexible applications. And that's why understanding polymorphism is crucial in object-oriented programming. All right, let's explore encapsulation. Encapsulation is a fundamental concept in object-oriented programming that essentially binds data and methods together into a single unit, which we call a class. It also plays a crucial role in restricting access to the inner workings of that class using access modifiers like private, public, and protected. For example, imagine a banking application. We want to keep the account balance secure and prevent unauthorized access or modifications. So, we make the balance variable private, which means it can't be accessed directly from outside the class. Instead, we provide a public method like getBalance. That allows controlled access to that data. This approach ensures that the account balance can't be changed arbitrarily, maintaining the integrity of the data. It also encapsulates the details, so users or other parts of the program only interact with the data in a safe and controlled manner. So, in summary, encapsulation helps us protect data, restrict unauthorized access, and keep our code more secure and manageable, aligning perfectly with the overall theme of writing robust, maintainable software. So, let's talk about abstraction. Abstraction is all about hiding the implementation details and showing only the essential features. Think of it as a way to simplify complex systems. We often use abstract classes and interfaces to achieve this. They allow us to define what needs to be done without getting into how it's done. For example, in a payment gateway system, when a user clicks Pay Now, they see only the final action. But behind the scenes, the system handles a lot more. It performs payment verification, checks for fraud, communicates with the bank, all without the user needing to know or see those details. This is a perfect illustration of abstraction in action. It keeps things simple for the user while managing complex processes behind the scenes. So, in essence, abstraction helps us focus on what the system does, not how every single detail is executed. It's a key concept in designing systems that are both simple to use and flexible to develop. Let's take a closer look at access modifiers and what they do. On this table, you'll see the four main types: public, private, protected, and default. Public members are accessible everywhere, meaning any part of your program can access them. Private members, on the other hand, are restricted to within the class itself. Only methods inside that class can see and modify them. Protected members are a bit more flexible. They're accessible within the same package and also in subclasses, even if those subclasses are in different packages. Lastly, default access, which we sometimes just call package private, means the member is accessible only within the same package, not outside it. These modifiers are crucial because they control the visibility and accessibility of classes, methods, and variables. This helps us enforce encapsulation, ensuring that sensitive data is protected and that different parts of our application interact in a controlled way. For example, in large enterprise applications, you'll often see sensitive fields like passwords or account numbers marked as private. This is a security best practice, keeping sensitive data hidden from other parts of the application that shouldn't access it directly. So, when we talk about access modifiers, think of them as the security gates for your code. They define who can see or modify different parts of your program, helping us maintain integrity and security across our applications. Let's talk about overloading and overwriting. Overloading happens when we have the same method name but different parameters. For example, we might have an add method that takes 2 integers and another that takes 3 integers. It allows us to perform similar operations with different input types or quantities, making our code more flexible. On the other hand, overriding is when a child or subclass provides a specific implementation of a method that is already defined in its parent class. This is useful when we want the subclass to behave differently for a particular method, customizing its functionality while maintaining the overall structure. Now, a real-world example of overriding could be a logging system. Imagine we have different log methods, one that takes just a message, and another that takes a message plus an exception. The subclass can override the parent class's log method to handle these cases differently, perhaps formatting the output or adding additional context. To sum up, the key difference is that overloading is about having multiple methods with the same name but different parameters within the same class, offering flexibility. Overriding, however, involves redefining a method in a subclass to change or extend its behavior. Both are powerful tools for making our code more organized and adaptable to different needs. So on this slide, we're focusing on the this keyword, which is really important in Java. It refers to the current object instance within a class. Basically, whenever you're inside an object and want to refer to that specific object, you use this. Let's look at a real-time example with constructor initialization. Imagine we have a student class with a name attribute. When we create a new student, we pass in the name. Inside the constructor, we write this name equals name. Here, this name clearly refers to the name attribute of the current object, while the name on the right side is the parameter passed to the constructor. This use of this helps distinguish between instance variables and parameters that have the same name, which is quite common. It makes the code clearer and avoids confusion. You'll find this being used extensively in data transfer objects, or DTOs, as well as in entity classes, because it ensures that each object's data is correctly assigned and maintained. So to wrap up, the this keyword is essential for referencing the current object, especially when dealing with constructors and methods that have parameters with the same names as class fields. It keeps our code precise and understandable, fitting perfectly into the overall theme of object-oriented programming. All right, let's talk about the super keyword. When we see super, it refers to the parent class object. It's used to access parent methods and constructors from within a subclass. This is especially useful when we want to call a method from the parent class that we've overridden in the child class, or when we need to invoke the parent's constructor explicitly. For example, consider a real-time use case with a class vehicle that has a start method. Now, if we create a subclass like car that extends vehicle, and inside car's start method, we want to ensure that the vehicle's start gets called as well. That's where superStart comes into play. It lets us call the parent class's start method directly from the subclass. This concept becomes particularly important when extending framework classes, where you often need to ensure the parent class's setup runs correctly before adding your own custom behavior. So, in summary, super is a powerful way to access and invoke parent class behaviors, maintaining clean and efficient inheritance. It helps us build on existing functionality without redundancy, which ties directly into our overall theme of effective object-oriented design. A constructor is a special type of method used specifically for initializing objects. Unlike regular methods, it has the same name as the class it belongs to. Think of it as a setup process that runs automatically when you create a new object. For example, when you're creating a user account, You might write something like user equals new user, followed by the necessary details. The constructor then takes those details and sets the initial values for that user object. This makes sure that every new object starts off in a consistent state. So, in essence, constructors are essential for setting up objects properly right from the start. Let's take a closer look at constructors. First, we have the default constructor, which is a constructor that doesn't take any parameters. It's like creating an object with some default values. Then, there's the parameterized constructor, which allows us to set specific values at the time of creation, making the object more tailored to our needs. Now, in real-world scenarios, constructors are quite useful. For example, when creating a new database entity, like an employee, we might use the default constructor to set up a blank employee object with default values. Or, if we have specific information ready, like an employee ID and name, we can use the parameterized constructor to create a fully initialized employee object immediately. So, for instance, we might write employee E equals new employee to create a blank employee, or employee E2 equals new employee 101 test to create an employee with specific details. This concept ties back into our overall theme of object-oriented programming, showing how constructors help us efficiently create and initialize objects, making our code more flexible and easier to manage. All right, let's talk about static members. These are special because they belong to the class itself, not to any specific object. This means that you can access static members directly through the class name without having to create an instance first. For example, think about utility classes you might use every day. Take mathmax, which finds the maximum of 2 numbers. You don't need to instantiate a math object to use it. You just call it directly through the class. Similarly, in enterprise applications, you'll often see classes like logger-get-logger. Again, no need to create an object. It's all about the class level. Understanding static members is crucial because it aligns with our overall theme of efficient and organized code. They help us write cleaner, more accessible code by allowing certain methods or variables to be shared across all instances or even used without creating any instances at all. All right, let's talk about the final keyword in Java. When we use final with a variable, like a final variable, it means that once we assign a value to it, that value cannot be changed later on. So, in this case, final int max login attempts equals 5 indicates that the maximum number of login attempts is fixed at 5, and it can't be altered during the program's execution. Next, if we declare a method as final, it means that this method cannot be overridden by subclasses. This is useful when you want to lock down specific behavior and prevent any unintended modifications in child classes. And finally, when we declare a class as final, it means that this class cannot be inherited. So no other class can extend a final class, which helps in maintaining security or integrity of the class's implementation. In real-world applications, like security constants, using final helps ensure that important values, such as max login attempts, remain constant and reliable throughout the system. This way, we prevent accidental changes that could compromise security or stability. So, to summarize, the final keyword plays a crucial role in safeguarding our data and structure, ensuring our code remains predictable and secure. Let's talk about the string class in Java. It's an immutable class, which means once a string object is created, it cannot be changed. This makes strings very reliable and safe to use across different parts of your program. Strings are used to represent sequences of characters, like words or sentences, in a very straightforward way. In real-world applications, strings are used heavily in various scenarios. For example, in REST APIs, where data is exchanged over the web, strings are essential for handling request and response data. They also play a crucial role in JSON processing, which is common when working with APIs and data interchange formats. Additionally, strings are vital when performing database queries, as SQL statements are typically composed as strings in Java. To give you a quick example, you might declare a string like this: string username test, This simply assigns the value test to the variable username, which you can then use throughout your application. Understanding how strings are used and their characteristics helps us write more efficient and reliable code, especially when dealing with data input, output, and communication in our programs. Let's take a closer look at the table. It compares 3 types of string classes: string, StringBuffer, and StringBuilder, focusing on whether they are thread-safe and mutable. Starting with string, it is immutable, meaning once you create a string object, its value cannot be changed. This makes string inherently thread-safe because no one can alter its content after creation. Next, we have StringBuffer. It is both thread-safe and mutable, so you can change its content, and it safely handles concurrent access in multi-threaded environments. Then there's StringBuilder. It's mutable like StringBuffer, but it is not thread-safe. This means it's faster because it doesn't have the overhead of synchronization, but you need to be careful when using it in multi-threaded contexts. In real-world applications, especially in log generation systems where performance is crucial, we often choose StringBuilder because it is faster. For example, we might write StringBuilder log equals new StringBuilder. This allows us to efficiently build logs without the overhead of thread safety, which isn't always necessary in these scenarios. So to summarize, string is immutable and thread-safe, but less flexible. StringBuffer is both mutable and thread-safe, suitable for multi-threaded environments. And StringBuilder, while mutable, is faster but should be used carefully when thread safety isn't a concern. This understanding helps us pick the right class depending on our application's needs. Now, let's talk about the automatic memory management process, which is essentially a system that removes unused objects from memory. This process is crucial because it helps keep our applications running smoothly by freeing up space that's no longer needed. In real-time use cases, especially within large microservices systems, thousands of objects can be created per request. Without an efficient way to manage this, memory could quickly become overwhelmed. This is where garbage collection, or GC, plays a vital role. It actively helps prevent memory leaks, which occur when unused objects remain in memory and take up valuable space, potentially leading to system slowdowns or crashes. So, understanding how garbage collection works is key to building scalable, reliable systems. It's all about automating the cleanup of unused resources so developers can focus on the core logic instead of worrying about manual memory management. Now, let's talk about the mechanism to handle runtime errors using try, catch, finally, throw, and throws. These are essential tools in our programming toolkit to manage unexpected issues gracefully. For example, when we write code that might throw an exception, like dividing by 0, we use a try block to attempt the operation. If an error occurs, the catch block catches the exception and allows us to respond appropriately, such as displaying an error message. The finally block, if used, runs regardless of whether an exception was thrown or not, making it perfect for cleanup activities. Throw is used to manually generate exceptions when needed, and throws declares exceptions that a method might throw, so calling code can handle them properly. A practical example is in payment processing systems, where catching errors ensures users don't see system crashes, maintaining a smooth user experience. Essentially, exception handling helps us build robust applications that can recover from errors without breaking down. It's a fundamental concept that ties into creating resilient, user-friendly software. Let's take a closer look at the table on this slide. On the left, we have the types of exceptions, and on the right, some examples. For checked exceptions, an example is IO exception. These are exceptions that the compiler forces you to handle, usually because they involve external resources like files or networks. On the other hand, unchecked exceptions include things like null pointer exception. These are runtime exceptions that the compiler doesn't require you to handle explicitly. They often indicate programming errors, such as trying to access an object that hasn't been initialized. In the real-world use case here, think about a file upload system. When you open a file with file input stream, like in this example, you must handle the checked exception, IO exception. If the file isn't found or can't be opened, your program needs to respond appropriately, perhaps by alerting the user or trying again. So the key takeaway is that checked exceptions are for conditions you anticipate and can recover from, while unchecked exceptions usually point to bugs that need fixing. Understanding this distinction helps you write more robust, error-resistant code. Subscribe for Day 3 of Core Java Interview Series. Thank you all for being here and engaging throughout this session. I hope you found the content valuable and insightful for your interview preparations. Remember, consistent learning and practice are key to mastering Core Java. If you haven't already, do subscribe so you don't miss out on upcoming days and deeper dives into Java topics. Your participation truly motivates us to bring more quality content. Thanks again for your time and attention. Wishing you all the best in your Java journey and future interviews.